It's July 1964, and the Ranger 7 probe has just recorded the highest quality video footage of the surface of the moon for the first time ever. Equipped with 6 Vidicom broadcast cameras, Ranger 7 could send back this footage to NASA via analog radio signal. But there was just one issue. Due to the nature of analog radio signals, Ranger 7 was victim to interference via other strong signals like the sun's radiation. Luckily, there is a fix. Dr. Robert Nathan of NASA's Jet Propulsion Laboratory had the idea to clean the distorted signal using computers, specifically the IBM 7094. And it worked. Their procedures stretched picture contrast and could improve picture resolution by up to 2,000 times. Thus, the digital age of photography was born. Well, in a way. Just a few years before Ranger 7 went to the moon, another scientist at JPL, Eugene Lally, had the idea to record image data using an electronic sensor rather than through a tube. He drew up the design for what was called a Mosaic array photodetector, which was a series of photodetectors in a grid, effectively designing the first image sensor. Later, he would work with Bell Labs and then Fairchild Semiconductors to produce the first prototype. However, the project would go no further, as Lally had other projects to work on at the time. Instead, he would ask Fairchild to give this idea to Kodak, for them to design their own camera using the sensor. But that's a story for another time. At the same time, in 1963, Dr. Frank Wanless was working on a new type of logic circuit that would combine both N-type and P-type semiconductors. This type of circuit would be known as CMOS, or the complementary metal oxide semiconductor. CMOS, as seen in this diagram, allows one transistor to turn on while another turns off. This design greatly reduced power consumption due to the fact power was only consumed when gates were switched on or off. Production cost was also much less compared to similar logic circuits at the time. It wouldn't be till much later, in 1993, that CMOS would be utilized to produce the first image sensor of its kind. But more on that later. 5 years after Ranger 7 went to the moon, 2 scientists by the names of George E. Smith and Willard Boyle were tasked by the VP of Bell Labs, Jack Morton, to work on an alternative to magnetic bubble memory. Bubble memory used magnetic film to store non-volatile memory in sections called, well, bubbles. Having MOS memory and diode arrays in mind, they would create the CCD architecture. This design laid a series of MOS capacitors in a row to allow a charge to step from one capacitor to the next. This, essentially, was an 8-bit shift register. Much like the origins of the CMOS sensor, the CCD sensor was not originally used to capture images. Michael Tompsett would be the first person to realize that it was photosensitive. And, with Gil Amelio and George Smith, they would demonstrate its ability to capture a crude image. The first image recorded was this: CCD on an oscilloscope. Not the prettiest picture in the world, but it was a great start. The patent for CCD as an image sensor would be filed by Tompsett a couple years later in 1971. And so, CMOS and CCD architectures have presented themselves as the 2 main ways to capture images via electronic sensors. Well, originally it was just CCD. You see, CCD at the time was much easier to produce. CMOS required multiple transistors to fit in a very small space. The technology at the time could not make something so small, and of course, the other reason is CMOS was only intended to be used where MOSFETs were used. Regardless, both sensors would flourish in their own way. So how did these sensors work? First, let's start with CCD. As a side note, I am assuming that you know how basic electronic components work. I am not a professor and I don't have hours to explain everything. So look whatever else up that you need. There are two main ways CCD arrays are situated. The first array is known as a linear array. This is where multiple photodiodes are in a straight or interlacing pattern. This array is perfect for when the subject is moving in one direction or not at all. Each of these diodes share a common readout register, which is also light sensitive. Because of this, the readout register must also be coated in a light shield so there's no interference. Pixel size is directly related to the photodiode size, and resolution is inversely related to pixel spacing. So in other words, bigger diode means bigger pixel. Smaller spacing means faster readout, and so on. The second array is the full frame array. With this array, photodiodes are read line by line in one large grid and read through one common serial register. This greatly improves quantum efficiency, or how effectively the sensor can convert photons into usable data. This makes memory mapping simple, at the cost of, production cost, that is. Again, it's very difficult to fit that many diodes into one small area when the technology at the time hasn't caught up to your design. CMOS, on the other hand, is a much more complicated architecture. With CMOS, each diode can have multiple transistors, leading to more control over the image and power consumption. As stated before, the most basic design of CMOS was one transistor is on and the other is off. This still reigns true, but way more complex. As you can see in the diagram, there is way more going on than CCD. Rather than a row of diodes connected to a common register, the register is connected individually to each diode, and each diode has its own transistor, and so on. In the case of modern CMOS sensors, the processor can have complete control over each pixel. The camera or device using these sensors could utilize variable frame rate to capture fast-moving objects in a flash, or, in low-light situations, read each pixel one by one to get the best picture quality. Of course, this all happens very fast and you don't even notice it, but on a small technical level, that is what it does. Although this is still true for CCD, CMOS has way more control and a much larger range, as well as other factors like the aforementioned way less power consumption. The explanation of both of these types of sensors is very simplified. If you'd like more in-depth information on how these work, I suggest the book CMOS, CCD Sensors and Camera Systems 2nd edition by Holst and Lomheim. It is a little outdated. It was made in the mid-2000s, but all the basics are there. So where are we today with these sensors? Well, it's mostly just CMOS, as it boasts way more control and way less power consumption than its counterparts, which is perfect for your cell phone camera or the cameras on your laptops. Since the late 2000s, this is where most of these sensors have ended up. CCD has fallen off substantially in recent years. Well, it's basically non-existent now, but historically it was the best and basically only sensor for the job. Almost every consumer and professional grade camera used these sensors from the 70s up until the late 2000s. It wasn't until the early 2000s that technology finally caught up to make CMOS sensors a possible alternative. And then, in the early 2010s, most companies slowly phased out CCD in favor for CMOS. This wasn't without its setbacks, however. CMOS had its slew of issues initially, with excessive glow or bloom, which is that sort of glowy effect around photos. You can probably see some a little bit maybe up there, if I don't color correct and do everything properly up there. as well as rolling shutter issues. Nowadays, this is basically non-existent. As a bit of a side tangent, the result of the smartphone boom in the early 2010s, consumers gradually shifted away from using a dedicated camera like this one, or the one I'm using to record this video, for this. But why is this? Well, as most people would agree, it's a lot easier to carry this around, which is basically a catch-all of functionality, rather than this, which just takes photos. As it turns out, unsurprisingly, consumers would rather have ease of access and memories wherever they go, along with using their phone for other things, rather than having a larger sensor or a dedicated camera. Me personally, I would rather choose the camera because I like cameras. Unless something new comes around, these sensors, both of them, will continue to be used. And for the case of CCD, it's probably more by preference or preservation, or maybe they're still floating around and they're in some cheap devices or something. Anyways, thanks for watching. All of my references to all my photos and all the information I've gathered is in the link below. Thanks, bye.